Hi everyone. In this video, I'm going to demonstrate mediation and moderation using SEM to accompany lecture 8 from PSYC 7505. So we're going to load the Lavon and SemTools packages. We'll be using Lavon for our analyses and SEM tools for some additional data handling with moderation models. All right, so we'll read in our data. Our data are called DAT for the mediation model. There's function file mediation.csv that has all of our variables in it. If we want to look at the data, we can see we have indicators for, and this is pretty much the same data we used for the SEM model. We have indicators for agency, intrinsic, extrinsic motivation, positive affect, negative affect, and our covariates. So usually we would start with a CFA model. I'm going to skip that in the interest of time and fit a model estimating our C path, that is our total effect, and then our mediation model. So the first thing we need to do is define our latent variables. This follows the example from class where we have intrinsic motivation, agency, and positive affect. We're testing is intrinsic motivation predicts positive affect, and that effect is mediated by agency. So we have our factor loadings for intrinsic, agency, and positive affect. To get an estimate of the total effect, I'm going to leave agency in the model, my mediator, and just allow it to covary with the other two variables. And then this will give me my estimate of my total effect, intrinsic motivation predicting positive affect. So we can fit our model now using a fixed factor method and look at our results. And so just to go through everything, this is the case. The model fits really, really well, a non-significant chi-square, which never happens. RMSEA is 0. So the model fit is really good. I want to focus more on the parameters today. So in particular, this regression, intrinsic motivation, our X, predicting positive affect Y. So our total effect is 0.453. And we can see the covariances of these other variables. So the more intrinsic motivation one has, the more positive affect. What we want to know is this relationship explained by failings of agency? So now we set up our mediation model. We define our latent variables the same way. We set up our latent regressions. First, we have our X variable, intrinsic motivation, predicting the mediator. As a reminder, regressions in Lavon are Y tilde X, outcome tilde predictor. So intrinsic motivation predicts agency, X predicts M, and that is the A path. So I'm going to use a label here. I'm going to call this A to represent the A path. If you wanted to use a different label, you could, but just for consistency. And then we have positive affect Y is predicted by agency, our mediator, and intrinsic motivation X. So the mediator M predicting our outcome Y, that's the B path. And then C prime here is the effect of X predicting Y. Now you don't have to put a label here. I'm going to use it and talk about this, but you don't have to do that. And then what we can do after that is define our new parameter. So we put the name of a new parameter, and this should be the name of something that's not used anywhere else in your model or your data set. Here I'm going to call it AB for the indirect effect. And then we use the operator colon equals. And from here, we have to use the labels we've created above. We can't put variable names or anything else in this. All has to be based on the labels of parameters. So here, A times B, this is going to multiply A and B. Multiply this regression path, intrinsic motivation predicting agency, times agency predicting positive affect. And I've also got down here, if we wanted to estimate the total effect, as a reminder, the total effect, which is what we saw here, this 4.53 is equal to the indirect effect, A times B, plus the direct effect, C prime. So we fit this model. And when we fit this model, again, this model I will mention has exactly the same fit. This is an equivalent model to the model we fit previously. But now in our regressions, we have our A pathway, intrinsic motivation predicts agency, that's 0.588. Our B pathway, agency predicts positive affect, that's 0.119. And our C prime, intrinsic motivation predicts positive affect, controlling for agency, 0.386. And then the last thing we have down here under defined parameters, this is our estimate of the indirect effect. So what this estimate is based on what we defined it, 0.588 times 0.119. And if we do that down here, we can see we get an estimate of 0.0699. This rounds to 0.07 or 0.070, exactly what we see here. So we get this estimate. Now, as a reminder, when we talked about methods of testing an indirect effect, this standard error and z-value and associated p-value, these are all based on assuming the distribution is normal, assuming there's a normal distribution of your of that indirect effect A times B. This is essentially like a Sobel test, and unless you have tens of thousands of people, this is not the most reliable method. This is not how we want to test it. So we would not look at this p-value. Instead, we might want to get a test of the indirect effect with bootstrapping. And so this code down here, it says fit 92. I'm going to call it B. We use the SEM command. We have our model, our data set, and then I've added on the end SE equals boot, and this will perform bootstrap resampling, and then bootstrap equals 5,000. It tells you to do 5,000 bootstraps. I ran this before I started the video. This takes about 3 minutes to run or so. It takes a few minutes. I ran it before just so I'm not sitting here silently and you're not watching a silent video for 3 minutes. But I ran this and we can look at the results. So if we ask for a summary, it should have worked. Hold on one moment. Make sure it's still in my environment. Oh, no, it didn't. Okay, well, we're going to start this running then. And I will pause the recording and resume when it finishes. It's the magic of video. Okay, we're back. So that finished running and we can look at our results up from our bootstrapped model. If we ask for a summary, the first thing I'll point out is bootstrapping. We do not bootstrap anything about model fit. Model fit is exactly the same. Nothing is bootstrapped. What changes are our estimates down here. With bootstrapping, it's not our estimates that change, but our tests of them. One thing to be careful of with bootstrapping is actually interpreting literally anything from this summary. I would not spend a lot of time on this because, and you'll see down here, with bootstrapping now, previously the p-value for our test of the indirect effect was 0.048. Now it's 0.0 with that Sobel test equivalent. Now with bootstrapping, it's 0.076. With bootstrapping, we don't want to use a p-value. We don't test and assess indirect effects with p-values for bootstrapping. We shouldn't pay attention to them. This is something you should ignore. It's built off the standard error here is that's reported right here is the standard deviation of the bootstrap distribution, but this again assumes that bootstrap distribution is symmetric, which we know it's not. So you should ignore this. Instead, to get the confidence interval, we use the parameter estimates function for our model. And this returns for every parameter in our model, the parameter itself. So this first was the factor loading for intrinsic 1. Any labels they have, the estimate, standard error, z, and p-value, and then this confidence interval is a bootstrap confidence interval. So for our indirect effect with 5,000 bootstrap samples, the bootstrap confidence interval is from 0.002 to 0.158. Because 0 is not within the confidence interval, we would reject the null and say there is a significant indirect effect. That this indirect effect here of 0.07 is different from 0. To do a Monte Carlo confidence interval, we're going to use the Monte Carlo Meade function. This is also from SemTools. And the way this works is you first put in what you want to compute in quotes. So here we want to compute A times B. As long as these, the values here are labels in your Lavaan object, and they are, A is this path, B is this one. And we say object equals the name of our Lavaan model. We will get our confidence interval. We're going to plot equals true. We'll plot out the distribution, what it looks like. And rep here, I'm doing 100,000. I'm basing this off of 100,000 replications. We're going to do at least 20 or 50,000. But we've got a minute. And you can see this is very, very fast. So in this case, what the plot looks like, you can see here's the distribution of the indirect effect based off of all of those. The middle of this distribution, the highest point, is our estimate of 0.07. And our confidence interval is from the bottom 2.5% about here to the top 2.5%. And our confidence interval, our confidence interval is returned right here. The lower limit's 0.0003, the upper limit 0.412. So again, 0 is not within here, we would reject the null. And so example 93, which I'm gonna skip example 93 for now. This is that example where we flip-flop the order. So now, looking at the mediation model, we can see now agency is X, intrinsic is M. And if you want to follow this along, this uses, the bootstrapping example uses the Levon default of 1,000 bootstraps without that bootstrap option, just to show you something different. And you can see model fit for this model will be exactly the same as we talked about in class. Parameter estimates will differ, and without longitudinal data, it's impossible to know which one is correct. For moderation, just as a quick demonstration, I'm going to use the RockChalk package to generate some data. Use the gen correlated data and generate 1,000 samples. Just to demonstrate with uncentered data, this is just in regression, doing a regression with uncentered data, looking at the interaction of X1 and X2. With uncentered data, we can see the p-value for that interaction is 0.6136. If we use the mean center function in RockChalk, we'll just mean center these variables and refit the model. If we do that, the p-value is 0.614. Exactly the same as what we saw up here. The t statistic, negative 0.505. It's exactly the same as what we saw down here. And if we residual center or orthogonalize, again, that p-value is 0.614. The t statistic, negative 0.505, is exactly the same. To demonstrate orthogonalizing in regression, sort of by hand as we call it. So we'll create a new variable, x1, x2, that is the product of x1 times x2 for everybody in the data set. And then I'm going to create a variable that's x1, x2, orthogonalized. So we're going to fit a regression here where we have that product term x1 times x2 predicted by x1 and x2. And this resid function here means I'm going to save the residuals from that as this new variable. So when we look at the new variable, our new variable, the residuals, this variable with the residuals has a mean of 0. Residuals always have a mean of 0. And if we look at the correlations, we can see that that variable is uncorrelated by definition with x1 and x2. Still correlated with y, but uncorrelated with x1 and x2. So if I fit a regression model with x1, x2, and that orthogonalized variable, I get exactly the same test statistic I saw before. So in regression, it really doesn't matter. Honestly, you should probably just use uncentered data. If we're going to do this in SEM, though, I'm going to read in data dat2. It's moderation.csv. So these data, we have indicators of positive affect, agency, and unknown causes. So we're interested in the relationship between agency and positive affect and how that's moderated by unknown causes. So we're going to create our orthogonalized terms. And I'm not going to do this by hand. We're going to use the indprod function. We specify the data set. And next we specify the names of the indicators for X, then the names of the indicators for the moderator. Match equals false will give me all pairs. So AGAT1 with, so in our agency 1 with unknown causes 1, agency 1 with unknown causes 2, agency 1 with unknown causes 3, agency 2 with each of them, and so on. Mean C false will turn off mean centering. Residual C is true. We'll use residual centering or orthogonalizing. And then the function will try to automatically name the names of the variables you create, or you can give them names. So here I'm going to name them int 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to give them those names myself. And now, if I ask for, so now in the data, we can see we have our original variables, and added on to that are our interaction variables. They all have means of 0. If we look at, let me pull this over here. If we look at a correlation matrix of the data, what we see is our positive affect items correlate with each other, so do our negative affect items and all of those. But these these interaction variables, they do not correlate with the agency or unknown causes variables at all. They correlate with positive affect, but not the others. They are totally uncorrelated. So the latent variables will be uncorrelated. So here, I'm skipping a step here just in the interest of time, which is usually we would fit a model, what I would call a main effects model, without the interaction variable in it and use that to assess fit. Again, just in the interest of time and simplicity, I'm going to skip that. But we would first, so we'll define our latent variables, agency and unknown causes. We've got our focal predictor, our moderator, and down here, positive affect or outcome, and then our interaction variable. And all those variables we created load on the interaction variable. Because we know that interaction variables uncorrelated with agency and unknown causes, we force those two covariances or correlations to be 0. Set up our regression equation. Positive affect is predicted by agency, unknown causes, and their interaction. And then the last thing are those correlated residuals. So for instance, interaction 1, 2, and 3 all involve something about the first indicator for agency. So they're all allowed to covary. Int 1 within 2, int 1 within 3, int 2 within 3. Next, int 4, 5, and 6, interaction 4, 5, and 6 all involve agency 2. 7, 8, and 9 all involve agency 3. 4, 1, and 7 all involve unknown causes 1, and so on. And so we allow all those covariances. And the other thing, just to simplify the model, is I've constrained the residual covariances involving the same item to be equal. So T1 here is everything, this is everything involving agency 1. Everything involving agency 2 is T2, all the way down. And then we just fit our model the same way we do before. We can look at our results. So a couple of notes about looking at these results. Remember, model fit is just going to be incorrect because there's all those zeros in the covariance matrix observed, and they'll also be in the covariance matrix for the data. The other thing I'll mention is the factor loadings for those interaction terms tend to be smaller on average. Their absolute value tends to be smaller. That's fine. We're not actually evaluating how well it fits. This interaction variable is really a trick to get at the interaction between agency and unknown causes. What we're interested in for our test of the regression is this slope right here. How does this interaction slope, so we can see that the slope is negative 0.087 and it's significant, P is 0.02. So unknown causes moderates the relationship between agency and positive affect. So here we see in this data set, agency is negatively related to positive affect. The more agency you feel, the less positive affect, and that's moderated by unknown causes. And down here, the covariances, we can see unknown agency in the interaction and unknown cause of the interaction, their covariance is forced to 0, and all the residual covariances are down here as well. If we do this with double mean centering, I'm going to use indprod again. I specify my data, indicators for X, indicators for the moderator. I'm going to say double MC equals true. By default, indprod will use a matched pair strategy. So we'll only create 3 indicators, agency 1 with unknown causes 1, agency 2, unknown causes 3, agency 3, unknown causes 3. And so we set up our model. So now we have agency, unknown causes, our interaction variable, our outcome variable, positive affect. In this case, we allow all the variables to correlate with each other, and we have our latent regression equation. Because we're using matched pairs, we don't need to include all those residual correlation or covariances because they aren't there. And so we can fit our model. And again, we're going to ignore fit. I'm just going to focus on these regressions here, or actually the covariances first. The first thing I'll point out is now the interaction variable. Covariance with the interaction variable and agency or unknown causes is not 0. As a matter of fact, there's a significant covariance or correlation with interaction and agency. And that's fine as long as we're accounting for it. The other thing we see is in this case, the slope of the interaction variable is negative 0.066. It's similar, but in this case, it's not significant. P is 0.091. There has been research that says this is probably because we used, not because of double mean centering, but because we used the matched pair strategy instead of the all possible combinations. That's been shown to have a little less power in some cases. And so that's probably where the discrepancy is. The last thing I'll talk about in this video is plotting and probing the interactions. So I can, for my orthogonalized variable, I can use the probe two-way RC, where I specify here the name of my model. Name X is the names of all the predictor variables, all the latent predictor variables. So agency, unknown, interact. Name Y is the name of the outcome variable. Mod var is the name of the moderator. In this case, unknown causes is the moderator. And then last is the values we want to plot and probe the moderator at. If you're using a fixed factor method of identification, -1, 0, and 1 are 1 standard deviation below the mean, and 1 standard deviation above the mean, which is just kind of a convenient thing. So if we fit this, if we do this, and we can look at the results, what we get is we get the simple slopes. So we get, this is the slope for agency when unknown causes are low, when unknown causes are moderate, and when unknown causes are high. And so we see, what we see is as the slope of unknown causes increases, as the slope of, as unknown causes gets larger, as people make more attributions for unknown causes, the relationship between agency and positive affect gets stronger, gets more negative. The more agency you have, the less positive affect you feel. We could do the same thing. We essentially the same thing, but using probe two-way MC for our double mean centered variable. In this case, the simple slopes are, I just looked at -1 and 1, and we can see, very similar results. This p-value is testing, is the simple slope different from 0? Not are they different from each other as a reminder, but if they're different from 0. And if you want to plot the results, there's a function called plot probe, where we give it the result of either probe two-way RC or MC, values of the moderator we're interested in, and it will plot our results. So here we have unknown causes at one low, moderate, and high, and you can see these dotted lines are different. And we can change the color of the lines and other things as we want to. So that's about it for mediation and moderation. I should mention the code includes an option using NLSEM. It's a lot of work, and it works sort of well. One of the things that happens is you have to actually run the model 3 separate times, each time using the previous set of results as starting values, and even then it gets a little dicey. But it is an option if you're interested in that LMS QML method. So thanks for listening in, and stay tuned for longitudinal next week.